Good afternoon. My name is Hwang. I'm a solutions architect at Cisco. Today I'm going to be talking about Cisco Science DMZ and then solution. So Science DMZ. Let me tell you a little bit about the Science DMZ. Science DMZ is architecture that is very prominent within the higher ed or research community. So I'm going to be talking about how ODR is being used. So you could think as a use case. And so second part of this presentation, we have a Booz Allen Hamilton, and they're going to talk about their security architecture that was originated from the Science DMZ architecture as a baseline. So the Science DMZ, the goal of the Science DMZ architecture is that if you have a large flow set, let's say elephant flow within the research community or campus customer perspective, you don't want to let it go through the 100 gig. Well, let's say you have a large flow, and then if you let it go through the firewall or IPS, that has been a problem because that's the kind of bottleneck. So if you drop some of the packets, then we started to see the performance dropping significantly. So Science DMZ 1.0, the architecture I call it 1.0, it came from the ESNet, and then in this diagram you could see, you have the campus and outside the firewall. And outside the firewall, we create the DTN data transport node. And the data transport node is directly connected to DMZ switch, typically OpenFlow switch, and then connected to router. The router has an ACL. So there was no the stateful firewall going on, but then you are able to send large flow without any hindrance because there's no TCP stateful devices like IPS or firewall. So this is the kind of a architecture 1.0. It worked okay. But then the problem was that if you think about the problem, a lot of, for instance, if it's the higher ed customers, the customer has the data sets inside the campus and then telling the researchers, hey, now you have to move your large data to DTN, the dedicated data transport node, outside the firewall. From the outside the firewall, you transfer again to other end nodes. That was too much work. So this architecture didn't really work well in university environments. And this is a Science DMZ, I call it 2.0. It was the Brocade and then Indiana University. They worked on this code, it's called SciPass Science DMZ. So the idea was that from the internal, you have a campus network and the network which is representing the external network. So let's say the traffic is coming from the internal network, campus network, coming into the OpenFlow switch, and then traffic is actually copied to the cluster of IDS. It was actually Snort. And then based on the IDS, in the IDS you put the kind of a wireless saying that, hey, if you match this type of traffic, and then it will call SciPass controller, which is OpenFlow controller, and OpenFlow controller will open up the ports. Well, it will program the flow, and then once it programs the flow, it will be like this. So it will no longer go to the firewall, but it will straight go out to the internet. So you could think as the bypassing firewall. So that's what Science DMZ was. And then I call it this one as a Science DMZ 2.0 because it was kind of automating it because there's IDS and IDS detects it. But then a little bit of the downside was that still inside of the IDS cluster of IDS, you actually had to put some sort of whitelist or ACL because detecting the large flow is not easy because you can. So based on this architecture, what it was based on the header information, and based on source and destination, we're going to assume that this is going to be the large flow. Okay. So from Cisco perspective, we wanted to create the architecture that customers can leverage. So we thought about what do we need to do in terms of Science DMZ, and then question we asked ourselves was that, okay, how can we secure our Science DMZ? Because it's good that we want to bypass the firewall. Still, once we connect, so we built this environment, and what we did, we started to see all the DDoS, coming into our environment. So we definitely knew we actually have to do something about the security. And so we thought about that, and then the way we wanted to do was we wanted to make a Splunk as a no-bound application on top of controller, opendaylight controller. And then because Splunk is our security devices, ASA, IDS, all these devices are feeding the Splunk, and based on the Splunk, we could actually create some of the trigger and then control the flows. So that's what we thought about. And also, we also asked ourselves, how can we identify large flow? And as I mentioned, identifying large flow, I think is still challenge. It's not easy to do it. So the way that we decided was we're going to just use globus. So globus is a tool that researchers use, and then once you log into the globus, the trusted endpoints are shown. So when researchers transfer the file, and it will set up the grid FTP, and then it will automate the grid FTP setup, and then you could actually do large data flow. So using the globus, what we did was, so this is kind of busy diagram, but in a nutshell, what's happening is all our devices, firewall, ASA, or our internal, everything is logging into Splunk. And then because ASA and all this, because we are logging on this Splunk, and then there are a lot of security alerts, and based on security alerts, we created the node-bound application, and then calling the opendaylight, and from the opendaylight, we are configuring, in this diagram, we have AS9K, so we are configuring AS9K with the black cooling and then putting the ACL. So in a nutshell, that's what we're doing. And then in terms of the globus large flow, let's say so globus is also, it's a data transport node, and because it has the API, it's actually, we made the globus log into Splunk. So when the transfer is actually to happen, let's say researchers said, hey, move this file here to here, endpoint 1 and 2, that information will be logged onto Splunk. And then because based on our search, we match it, and then we tell, in this diagram we have a Nexus 9K on, Nexus 3K, right below Internet 2, and they have the advanced layer 2 service. That's the OpenFlow switch, and then from there, we program this flow so that every traffic is not going to the source fire, but it's directly going out to the internet. So there were the two things that we did. And so this is just the, we thought the Splunk as an SDN application because it receives all the feed. So, and this is kind of a snapshot of our Splunk. So the first one, this is very small, so you cannot see, but that's the feed coming from the IDS. And then based on IDS, we have a high priority IDS event, and then we block the host immediately. And the second one is based on the SYN attack that the ASA is receiving. And based on that, we say, okay, if SYN attack, block host after 100 improper SYN and within 60 seconds. So that's based on that rule that we are blocking the ASA. And the third one is the block timeout. And then, because we don't want to block the host, because it may be the DDoS host may be compromised, but then after a certain time, it may be healed. So we wanted to put the unblock host time. So that's what we did here as an example. And this is the OpenFlow side on the Nexus 3K. So we could put source file IDS or firewall in inbound or outbound, and then just put some examples. It's not really in depth, so but if you have a question, I could answer that later on. And so this is another thing that, when we detected the DDoS from the Splunk, and we're controlling from the opendaylight perspective, opendaylight has many mechanisms to talk to AS9K router, and it has a BGP, and then we typically use netconf. So this has been 1 year old. So we did this demo at Cisco Live in 2015. So it's been around for a while. And so when we were using the controller, we thought, okay, we could use a BGP, but we just use the netconf and yang, and then, netconf, and then put the CLI commands through that static route, and then we put the black holing using that. And this is a screenshot, and the customer loved our solution because number one reason was that if you create the security design, and the traditional idea was that you bypass the firewall, but then you really don't know who's actually using what is being bypassed. But because we are logging from the DTN, the data transport node, which is globus, we actually know the user and amount of data actually transferred. And then based on that, how much is bypassed. So it was actually, in this diagram, we have the username, the top 10 globus username. So my colleagues and myself, and then we know exactly how much they sent, but we could also figure it out what kind of data was being leaked out or things like that. So this has been received very well. And then lastly, so we talked about, so what's next? So from internally, we thought about our roadmap, and then TrustSec was something that we wanted to do, implement on the Science DMZ, which I haven't done it, but I'm working with other partners working on this. But the reason that with the TrustSec was, the benefit of TrustSec is you could pre-populate your policies already based on certain tags. And then now, when you match certain traffic, you just impose certain SG tag, and then based on the tag, the security is applied. So it was kind of it's much faster reaction to the security threat. So this is something we are working on. But unfortunately, when I was submitting this, I was working on it, but I didn't finish it. But this is on the roadmap. And I think I'm going to skip, and I'm going to give mic to Emre.
Me, yep.
Let me just give you.
Thanks. All right, so good afternoon, everyone. My name is Emre Ertekin, part of the Cyber Futures team of the Booz Allen Strategic Innovations Group. And I'm here today to talk a little bit about a proof of concept that we developed in partnership with Cisco around an SDN-based cybersecurity ecosystem. So really the problem that we're trying to address with our proof of concept is the ability to rapidly detect an incident and respond to an incident. Or typically your incident, what's known as your incident response processes that are implemented by network operators. So if you look into the NIST framework for improving critical infrastructure cybersecurity, they talk and they categorize the different subphases that are associated with incident response. That includes your prevention, your detection, your response, and your recovery. So what do we mean by prevention of an incident? And that just basically encompasses making sure that you have the right people, processes, and technologies in place within your infrastructure to detect an event and then rapidly respond to it. The detection phase is, ensuring that, okay, if you have a SIM console, and then you're monitoring traffic that's coming into your infrastructure, that the rules are provisioned correctly, and ensuring that SIM basically flags any type of anomalous activities that are going on. Once that anomalous activity is flagged, you typically go and you perform incident triage, and then you actually engage your network forensics and malware forensics team to actually go and look into analyzing the incident, what happened with the incident, and then determining your initial course of response. And then you enter the last stage, your recovery stage, which includes your containment, eradication, and mitigation of your incident. So as you can tell, this entire process here, it's very manually intensive, and it requires a lot of human involvement. So for what we developed was this idea of our SDN-based cybersecurity ecosystem. And I'm going to move pretty rapidly through the slide, but we're happy to discuss this with anyone who wants to offline. But basically, you have your different threat actors that exist that launch different types of attacks on your infrastructure. The US CERT actually gives a good taxonomy of your different types of attack types. And once those attacks are launched on your infrastructure, you'll have different sensors within your infrastructure that provide telemetry information about the traffic that's coming into your network. And those sensors may be collecting statistics like net flow statistics, IPFix, or syslog data that is eventually fed into a SIM. From that SIM, you have a specific policy engine that goes and determines your appropriate response to that incident. And then through these controllers, you'll go and you'll implement those policies and those response actions. And so, again, we're looking to automate all of these components through this SDN-based cybersecurity ecosystem. So to do this initial proof of concept in partnership with Cisco, what we were looking at, as Tay mentioned earlier, was regarding addressing distributed denial of service attacks. And the reason why we chose, DDoS attacks have been around for a while, and there are different approaches to mitigating DDoS attacks that could include, just simple provisioning of firewalls within your infrastructure, to implementing data scrubbers on premise within your local network, to doing an outsourced data scrubbing service to your DDoS service provider. And so with all these different tools and technologies that you can use to prevent a DDoS attack, that policy engine that I talked about in the previous slide, we're trying to implement that knowledge within an automated capability to go and actually determine what is the best way to address and mitigate that DDoS attack, and then what is the best course of response. So the goal of SCE is to work with all those components together and determine what that best course of action would be. So I'm going to turn it over now to Michael, who's going to talk a little bit more about the details of our SCE architecture.
Thanks, Emre. So, I believe this one. Can you guys hear me? So, I think I have a few minutes here, so I'm going to try to go through some of these quickly. But as Emre said, we can go in more detail if people are interested. This is just showing a typical flow for a normal user trying to access a web server. Hitting the reverse proxy then going back to the back-end web server to provide that web server to the end user. And so what we're trying to do here, everything in this network is in our lab in a VMware environment, and all of these components are NFV products. We're collecting sensor information from 3 different sources. From the reverse proxy and the Apache web server, we're collecting syslog information. From the network devices, we're collecting NetFlow data. And then from the Firepower IDS, the Firepower Management Center is sending information about that sensor, and everything's being collected in Splunk. The CSR actually has a span port, which is feeding the data over to the sensor, which is then identifying different alerts. So what we're doing with this is that all of the sensor and feed information is coming into Splunk. Similar to what Tay mentioned, to what they're doing at the Science DMZ, we're using different algorithms within Splunk to be able to identify an event, and then that is attached to a response script, which is reconfiguring the network. And I'll go through the details of the different types of responses that we're implementing. But the last part is we want to log this data. So as the event gets identified, we're taking the response, we're creating a log file, which is collecting all of that information about what the event was, what response we took, and the time it took between when an event happened to the response. And all of that data is going into a log file, which is being fed back into Splunk, so that we're able to go back in time and look at that data and be able to understand what happened. So we're using different responses coming from Splunk. Splunk is using just a REST API to either the network devices, such as the ASA directly, but most of it is going through OpenDaylight. And we're using OpenDaylight because we get the benefit of having multiple southbound protocols that we can then reconfigure products using protocols such as BGP, NetConf, and OpenFlow. And so with the CSR, we're doing both NetConf and BGP FlowSpec, and we're using OVS to implement OpenFlow rules. So I'll go through a couple different types of events that we're identifying and how we're reacting based on those. So what's shown in the next couple slides is the sensor information is coming into Splunk right now. In what's shown in 2 is really just showing the reverse proxy, but we're collecting the information from all of the sensors, like I mentioned before. It's just a little bit less busy to show the one flow. But what happens is we have an adversary that is attacking the reverse proxy. Based on the syslog information, the NetFlow data, as well as the firepower information, we're determining at Splunk that an event has occurred that's triggering an alert, which has a corresponding script that is making a REST API call to OpenDaylight to parse out the source IP address of the attack source and creating a ACL that gets pushed to the CSR. Now, the ACL isn't a drop ACL. It's actually being used as a classifier and is classifying the data and marking it with a DSCP value of 8, the scavenger class. When that traffic gets to our open virtual switch, we have a flow rule already pre-provisioned that matches on that DSCP value and mirrors that traffic to a network forensic platform, but still delivers that traffic also to the reverse proxy. So we're actually just at this point doing further analysis because we've identified that this might be a malicious traffic, but we don't want to deny it yet. The other type of event that we're taking is a direct REST API call from Splunk to the ASA. Again, this is an ACL to drop traffic at our edge firewall. The third type of response that we're doing is a REST API call from Splunk to OpenDaylight to create a BGP update, which is using FlowSpec to inject a new prefix into our edge router. And we're using an extended community of a rate limit of 0 to do drop traffic. So instead of dropping at our firewall, we're now dropping at the edge router using BGP FlowSpec, and that can also be sent into the service provider network to drop the traffic in that environment if we have too much bandwidth coming and filling up our pipe at the edge. So I won't go, given time, too much into the lessons learned, but a lot of this has to do with the protocols and interfaces that network devices are supporting today. So we've looked at a lot of different products and a lot of different capabilities, and there still is a lack of support for a lot of these protocols that we'd like to be able to use within OpenDaylight, such as netconf, Yang. The only common thing is that everyone supports a proprietary-based CLI interface. And then there's the model support. So even if devices support a netconf interface, they might not have the Yang models that allow us to be able to reconfigure the types of commands that we might want to be able to push out. There's obviously a lot of work going on there, and we're seeing progress with every new version of code that's coming out from a lot of these vendors, but there's still a lot of work, I think, in that area. And then the last bullet here just talks a little bit about that while most vendors are implementing virtual devices now, they're not always the same as their hardware-based counterparts, and so there is still some work in that area as well that we've identified going through this. And just the last thing is that where we're trying to go next is to integrate additional network devices into this ecosystem, identify additional sensors that we want to add in to pull in more information. Right now we're using Splunk, but there's a ton of different analytics tools out there that we could be doing additional analytics on that information. And then just looking at other use cases. So I showed the OpenFlow mirroring situation. You can easily set up a honeypot off of that OpenFlow switch and be able to route traffic using dynamic OpenFlow rules to route to a honeypot instead of just monitoring or mirroring the traffic. So there's a lot of different use cases that we also want to add into this environment. And with that, I guess if anyone has any questions for any of us. All right, thank you, Emre.
Because it was kind of automating it because there was IDS and IDS detects it. But then a little bit of the downside was that still inside of the IDS cluster of IDS, you actually had to put some sort of whitelist or ACL because detecting the large flow is not easy. Because you can based on this architecture, what it was based on the header information, and based on source and destination, we're going to assume that this is going to be the large flow. Okay. So from Cisco perspective, we wanted to create the architecture that customers can leverage. So we thought about what do we need to do in terms of Science DMZ, and then question we asked ourselves was that, okay, how can we secure our Science DMZ? Because it's good that we want to bypass the firewall. Still, from the internal, you have a campus network and the network which is representing the external network. So let's say the traffic is coming from the internal network, campus network, coming into the OpenFlow switch, and then traffic is actually copied to the cluster of IDS. It was actually stored. And then based on the IDS, in the IDS, you put the kind of a wireless saying that, hey, if you match this type of traffic, and then it will call CyPass controller, which is OpenFlow controller, and OpenFlow controller will open up the ports. Well, it will program the flow, and then once it programs the flow, it will be like this. So it will no longer go to the firewall, but it will straight go out to the internet. So you could think as the bypassing firewall. So that's what Science DMG was. And then I call it this one as a, Science DMG 2.0, flow without any hindrance because there's no TCP stateful devices like IPS or firewall. So this is the kind of a architecture 1.0. It worked okay, but then the problem was that if you think about the problem, a lot of, for instance, if it's the higher ed customers, the customer has the data sets inside the campus and then telling the researchers, hey, now you have to move your large data to DTN, the dedicated data transport node, outside the firewall. From the outside firewall, you transfer again to other end nodes. That was too much work. So this architecture didn't really work well in university environments. And this is a Science DMG, I call it 2.0. It was the Brocade and then Indiana University. They worked on this code, it's called CyPass Science DMZ. So the idea was that, good afternoon, my name is Hwang. I'm a solutions architect at Cisco. Today I'm going to be talking about Cisco Science DMZ and then solution. So Science DMZ, let me tell you a little bit about the Science DMZ. Science DMZ is architecture that is very prominent within the higher ed or research community. So I'm going to be talking about how ODR is being used. So you could think as a use case. And so second part of this presentation, we have a Booz Allen Hamilton, and they're going to talk about their security architecture that was originated from the Science DMG architecture as a baseline. So the Science DMG, the goal of the Science DMG architecture is that if you have a large flow set, let's say elephant flow within the research community or campus customer perspective, you don't want to let it go through the 100 gig. Well, let's say you have a large flow, and then if you let it go through the firewall or IPS, that has been a problem because that's the kind of bottleneck. So if you drop some of the packets, then we started to see the performance dropping significantly. So Science DMG 1.0, the architecture I call it 1.0, it came from the ESNet. And then in this diagram, you could see, you have the campus and outside the firewall. And outside the firewall, we create the DTN data transport node. And the data transport node is directly connected to DMZ switch, typically OpenFlow switch, and then connected to router. The router has an ACL. So there was no the stateful firewall going on. But then you are able to send large